Now, statistical analysis of a univariate sample is obviously much simpler than that of a multidimensional one. This is not only true for the qualitative comparison of a sample with a parameter-dependent PDF, but also for the quantitative parameter inference, especially when the PDF is distorted by the measurement process and a Monte Carlo simulation is required. The direct maximum likelihood method cannot be applied. The parameter inference then happens by comparing histograms, with the problem that in multidimensional spaces, the number of entries can be quite small in some bins. That is why we have an interest to reduce the dimensionality of the variable space by appropriate transformations, of course, if possible, without loss of information. So that is one of the first things we'll try to look at in this lecture. The reduction of the number of variates. Let's try to start with consider two variables in a single linear parameter. So a probability density function of two variates with a linear parameter dependence can always be written in the form f of x comma y given theta equals v of x comma y times 1 plus u of x comma y. Now the log likelihood for observations is simply given as and this is essentially a function of only one significant variate, because log of v does not depend on theta and can be omitted. Our maximum likelihood of theta, maximum likelihood estimate of theta for a given sample with the log likelihood depends only on the observations. But of course, ui is nothing but u defined at xi, yi. And the analysis can be based on individual quantities or a histogram. So the simple form of this relation suggests that the analytic form of the PDF of u is not needed for the parameter inference. Only the experimental observations enter into the likelihood function. But this nice property is lost when acceptance and resolution effects are present. And this is usually the case. So in this situation, the linearity in theta is lost because we are forced to renormalize the PDF. Nevertheless, we gain by the reduction to one variate u. If the detector effects are not too large, the distribution of u still contains almost a complete information relative to theta. Let's see how this can be generalized to several variables and parameters. So let's say vector x denotes n variates. In such case, first of all, the generalization for the PDF is quite straightforward. And again, we can reduce the variate space to a single significant variate, which is u in this case, without losing relevant information. Now, if simultaneously p parameters have to be determined, we'll also need p new variates, u1 all the way up to up. And basically we have a sum over p's, so up of x times theta p. Now, of course, the procedure only makes sense if the number of parameters is smaller than the dimension of the variate space. So let's consider one example. So if we consider f of xyz given theta as 1 by pi square plus y square plus z square, we take a square root, plus x plus y cube times theta, where xyz collection of points that lie within the unit sphere. So this PDF depends on 3 variates and 1 parameter. Now, for a given sample of observations in the 3D Cartesian space, we want to determine the parameter theta. So if we introduce substitutions, u equals x plus y cube, x square plus y square plus z square, square root, and the modulus of u is less than equal to root 2. V is simply x square plus y square plus z square square root, and we keep z as z, so v must be between 0 and 1. So this leads to a So these substitutions, they lead to a new PDF. Let's call it G prime UVZ. So we can write G prime UVZ given theta equals V by pi times 1 plus U theta times basically the Jacobian for the transformation. After integrating out V and Z, we can get the marginal PDF for U alone. Now this integration is not analytically feasible. It has to be done numerically. But we do not need to compute G explicitly, as we have seen moments ago. So we are able to determine the maximum likelihood estimate and its error from the simple log likelihood function of theta, which is just the log of L theta, sum over I of the log of 1 plus ui theta. So this example that we have investigated is especially simple because the PDF depends linearly on a single parameter. And linear dependencies are quite frequent because distributions often consist of a superposition of several processes. And the interesting parameters are the relative weights of those. For the general non-linear case, we restrict ourselves to a single parameter to simplify the notation. And we expand the PDF into a Taylor series at a first rough estimate. So as before, we choose the coefficients ui as new variates. Now, neglecting quadratic and higher terms, the estimate depends only on the new variate, in this case just u1x. Which is a simple function of x. So if the linear approximation is insufficient, a second variate should be added, which would be u2 in this case. Alternatively, the solution can be iterated, and then the generalization to several parameters is straightforward. Now we'll shift gears a bit and focus our attention on what are known as nuisance parameters. So frequently, a PDF, this will be denoted by f of x given some theta and some nu. It contains several parameters from which only some are of interest. Whereas the other parameters are denoted by the vector nu, these are unwanted, but influence the estimate of the former. These are called nuisance parameters. So if you know the PDF of a nuisance parameter vector, that is the prior of new, then we can eliminate new simply by integrating it out. So and we can obtain this probability density function as a result, which only displays the dependence on thetas. And this way we obtain a PDF depending solely on the parameters of interest. The corresponding likelihood functions theta is given by this integration of the overall likelihood function weighted by the prior probabilities of the nuisance parameters, or in other words, the integral that we have just highlighted above. Now, if the PDF is of the form just to simplify the discussion, we are using theta and nu instead of the vectors theta and nu. So, if the PDF can be cleanly factorized into a theta dependent part and a nu dependent part, then we can write the likelihood as a product with L theta of theta is the product of overall i's, and this piece is independent of the nuisance parameter. So as an example, let's look at the elimination of a nuisance parameter by factorization of a two-dimensional normal distribution. So we look at a sample of n points xi, yi, where I goes from 1 to capital N, and these points follow a normal distribution. we see that we can, since the exponential as its argument contains a sum, we can split it into a product of exponentials and write this as theta is the parameter which we are interested in. So the normalized x distribution depends only on theta. Whatever value nu takes, the shape of the distribution remains always the same. So we can estimate theta independently of nu. And the likelihood function is proportional to a normal distribution of theta. With the estimate theta hat is given as the mean of the sample points. Sometimes we manage by means of a parameter transformation to bring the PDF into the desired form, where the PDF basically factorizes into two parts which depend separately on the parameters theta and nu bar. Let's say we have a Gaussian likelihood. Which is proportional to exponential of minus a square theta minus theta hat square minus 2ab rho theta minus theta hat nu minus nu hat plus b square nu minus nu hat square. We see that right now we can't factorize it, but if we do a transformation, say nu bar equals some c1 plus c2 nu, then with suitably chosen c1 c2 we can have a likelihood function that parameterizes in the new parameter pair, that factorizes in the new parameter pair theta and nu bar, and the transformation can lead to, so for suitable c1 c2, so it turns out that this procedure yields the same result as simply integrating out the nuisance parameter, and as the profile likelihood method, which we will discuss next. The result is interesting in the following respect, is that in many situations the likelihood function is nearly of Gaussian shape. Therefore, integrating out the nuisance parameter, or better to apply the profile likelihood method, is a sensible approach in many practical situations. The nuisance parameters are a problem only if the sample size is small. So let's look at an example of eliminating a nuisance parameter by such restructuring or transformation of variables. So if you consider radioactive radiation, then the absorption factor for radioactive radiation by a plate is determined from the number of events. Let's call them R1, R2, which are observed with and without the observer within the same time intervals. And these numbers follow Poisson distributions with mean values, let's say rho 1 and rho 2. So we have F1 R1 rho 1 equals minus rho 1 to the power R1 by R1 factorial. And similarly F2 R2 rho 2 e to the power minus rho 2 to the power R2 by R2 factorial. Interesting parameter is the expected absorption, which is given as rho 2 by rho 1. In the first approximation, we can use the estimates R1, R2 of the two independent parameters and their errors to calculate the uncertainty. So we can give theta hat as R2 by R1 and delta theta hat square by theta hat square would simply be 1 by R1 plus 1 by R2. For large numbers, R1, R2, this method is justified, but the correct way is to transform the parameters of the combined distribution. So, combined distribution basically has f of R1, R2 given rho 1, rho 2. So we'll transform this into independent parameters. Theta equals rho 2 by rho 1, nu equals rho 1 plus rho 2. Our transformation gives f tilde of R1, R2 that theta and rho and one can see in the likelihood function we can do a factorization. Then if you look at the log likelihood, of theta, and that is given simply like this. Instead of a parameter transformation, sometimes it is possible to eliminate the nuisance parameter if we can find a statistic which is independent of the nuisance parameter, or in other words, ancillary with respect to that parameter, but dependent on the parameter theta in which we are interested. Then we can use the PDF for this new statistic, which per definition is independent of nu, to estimate theta. But in such a case, we may lose information because this new statistic, let's call it y, is not necessarily sufficient relative to theta. So next, we turn to approximate solutions. So there are certain schools of thought that propose to replace the nuisance parameter by its estimate. This basically corresponds to a delta function for the prior of the nuisance parameter, and because of that it's a bit dangerous. It leads to an illegitimate reduction of the error limits whenever the nuisance parameter and the interesting parameter are correlated. Now note, a correlation always exists unless a factorization is possible. In the extreme case of full correlation, the error would shrink to zero. A much more sensible approach to eliminate the nuisance parameter uses the so-called profile likelihood. And to explain it, we can give an example with a single nuisance parameter. The likelihood function is maximized with respect to the nuisance parameter as a function of the wanted parameter. So then we insert this into the likelihood function, and that basically gives the profile likelihood. Which depends solely on theta. This method has the great advantage that only the likelihood function enters and no assumptions about priors have to be made. It also takes correlations into account and the error interval of the profile likelihood. So, which is delta log of the profile likelihood, setting that equal to half. That can be found by drawing tangents of the curve delta log equals half parallel to the new axis. And these tangents include the error interval. In the limit of a large number of observations where the likelihood function approaches the shape of a normal distribution, the profile likelihood method is identical to restructuring and factorizing the likelihood. Now, if the methods fail, the methods that we have discussed so far, then we are only left with two options. Either we give up the elimination of the nuisance parameter or we integrate it out. So that simple integration over all the entire range of these nuisance parameters, it implicitly contains the assumption of a uniform prior of nu, and therefore to some extent depends on the validity of this condition. However, this turns out to be a reasonable approximation in most cases, and the effect of varying the prior is usually negligible, except when the likelihood function is very asymmetric. Now, it is not always possible to eliminate the nuisance parameter in such a way that the influence of the method on the result can be neglected. So, when the likelihood function has a complex structure, we are obliged to document the full likelihood function. So, in many cases, it is possible to indicate the dependence of the estimate theta and its error limits on the nuisance parameter explicitly by a simple linear relation. Give us theta hat equals theta at 0 plus So this is the estimate. And theta 1, 2 are the error limits. Usually the error limits will show the same dependence as the maximum likelihood estimation, which means the width of the interval is independent of the nuisance parameter. However, publishing a dependence of the parameter of interest on the nuisance parameter is useful only if nu corresponds to a physical constant and not to an internal parameter of an experiment, such as the efficiency or background.